Welcome to the second half of the two-part episode of Zeroing In with Professor Thejesh Bandi. A physicist by profession and an engineer at heart, Professor Bandi led the scientific group behind the development of the first ever indigenous rubidium atomic clock of India at ISRO. While in the first part of this episode, Professor Bundy elucidates on the details of building an atomic clock and the fundamental science behind them, in this second half, we discuss at length about the impacts of such groundbreaking technologies on the outside world. With his nourishing insights and immense experience, while also keeping his passion for science and innovation thriving, Professor Bundy takes us for a further fascinating dive where he details upon a first hand experience of working at some of the finest institutes of the world.
uh, Generally, why does country needs a time standard? Every country needs a time standard. The question is, why do they need so? Why does every country need to have a time standard? Why does an atomic clock is required for that time standard, and each country requires an atomic clock for its own time standard? What is the role of it, and why the implication is so strong on it, and why are countries focusing on that?
That's a very good question because you see the idea is I mentioned that we have defined time since 1967 as these many oscillations of cesium atom. Now the definition stands good. Now who is going to contribute whether that definition is holding good or not, right? So there are about 90 laboratories around the world and about 400 clocks or so altogether. Everybody, they measure how good their clock is behaving and then send that information to an agency based in Paris, which will define the SI time, and they maintain that SI time. They send all the information of how these clocks are behaving in each of their labs to BIPM. Okay. So that is where they measure something called TAI, Time Atomic International. Okay, which is basically the weighted average of all these clocks around the world, right? So that's when you know, okay, this is my TAI, and this is my Greenwich Mean Time zero, okay? And at different time zones, this is how the local time is. It's a two-way communication if you think of it, right? Now, say for example, there is NPL in UK, there is NPL in Delhi, and there is USNO here in US. So what all these agencies do is that they maintain local time. They give this information to BIPM, how good their local clocks are, right? And the BIPM takes the weighted average of all these clocks. How much is the drift, and how stable these clocks are, and so on. Based on that, they release something called a circular T every fortnight, which means based on the weighted average of all these clocks from around the world, this is how the defined time is, okay, or the derived stability and therefore the time is. Now all other labs would in turn compare where do they stand with reference to the weighted average time. Then they will make the corrections necessary. If the clock was drifting too strongly, they would correct for it. Okay. So again, they will send the information back to BIPM. So this is a closed loop condition that you need to satisfy in order to keep on measuring and maintaining the time. So therefore, you need many labs in order to contribute.
Yeah, coming back to the engineering point of view, I know that you have been working on rubidium atomic clocks for most of your career, and cesium and rubidium are the two common elements used for atomic clocks. So I wanted to ask, why is there a preference to use these two elements, or are there any other alternatives available to rubidium and cesium?
Another way to look at this particular question is, why did we choose only certain elements? When I look at the periodic table, I see 100 elements there. Why can't we make clocks out of all of them? Right? In principle, yes, it's possible to make clocks using any atom, right? But look at the picture of the spin, the quantum property. In order to be able to measure spin, in a much more effective manner, you need that single electron in the outermost shell, or a single electron, which can actually give you um, the leverage in order to measure spin in a very precise manner, right? And therefore, the alkali metals, where you have the um, lone electron in the outermost orbital shell, therefore these atoms were chosen in the first place. That means, hydrogen starting, and then rubidium, cesium. People have measured sodium and things like that, but there are certain other engineering challenges, in the sense how well you can confine these atoms, right? And what are the electronic transitions that you can, how accurately can you measure them? That's one thing. Another aspect is, you need to know the energy level structure of all these atoms so very well. Only then you can measure the clock transition. Okay. When I say clock transition, what it means is, there was a question initially that, what are hyperfine transitions, right? So whenever we say it's a hyperfine transition, although we talk of two ground state levels, these are not only two ground state levels. It has degenerate states. Degenerate means that when you subject this atom in an external magnetic field, these levels would further split into their Zeeman levels. Okay. Now, among those, different levels that are further split, okay, as per their degeneracy, the MF00 transition, which in other words will not have any effect due to the first order magnetic field. When we say first order, that means a fixed magnetic field. Second order would be time varying magnetic field. Okay. A first order magnetic field, when you subject, these two levels that we are talking of, they won't shift, right? So that is what we choose as clock transition. Okay. Now, taking any particular atom, we need to know well about this particular clock transition. Only then we can make the electronics and the particular experiment in order to extract this atomic signal out of it, and so on. So now, therefore, the alkali metals are preferred. Okay, this is to do with the microwave standards. These days, people are doing optical clocks as well, which means there is aluminum clock, mercury ion clock, aluminum ion basically, and then there is strontium clock, strontium lattice clock, strontium ion clock, the ytterbium clock, right? When I say ion, what it means is that this has a closed shell. Closed shell means the two electrons, spin up and spin down, are in the outermost shell, which means there is no free electron in order to do the interrogation. Now, when you strip out one electron from it, then it becomes an ion, a positively charged, right? So, but in an ion, you have that outermost free electron again. So, therefore, you can take any atom and ensure that there is free electron in the outermost shell, by making that as an ion, right? And then you can do the atomic clocks. That is possible. But the energy transitions should be very well known before we start. To answer further that particular question, people want to now, they're working on nuclear clocks. Okay. Thorium is the atom that is chosen in order to make the nuclear clock. Okay. But there is huge amount of research that's going on since last 10 15 years in order to understand this energy level structure of thorium atom. So if you want to use any atom in order to build a clock, first of all, you need to understand the atom very well.
Yeah, that makes sense. We have been covering a lot of part of the applications that atomic clock has. So we see that it's being used in a lot of day-to-day activities on the background of it. And we also saw that the kind of research required is very, very precise and very, very expensive if it comes to it. So I'm assuming not every country has the ability to build atomic clocks on their own. So can you shed some light which few countries have been working on this, and does India have its own atomic clocks? We have been hearing about news for last 5 6 years, but we haven't had anything concrete about it.
This is kind of an insider information, but I'll be glad to share this because it's a proud moment that India has its own atomic clock now. And along with my team and a lot of support within ISRO, that's what I was able to contribute as well in order to develop an Indian rubidium space clock. Pretty soon, perhaps the very next launch, the Indian space clock would be launched. Okay. And there are developments for the hydrogen maser, ground based clocks as well. Not a very big scale like what China has been able to work on. Okay. There are many institutes in China. The clocks are being developed, and there is a pretty fantastic progress over there. In India, yes, the clock is all done now. Pretty soon, it would be launched. Germany, there's a lot of development. Japan, there's a lot of development. Switzerland, UK, France, almost all the countries that I know are pretty active in this particular field. Although many countries are catching up a bit late, I must say, and therefore you don't hear about these news a lot. But everyone is now catching up because everyone realized that this is such an important technology to have for any country to develop further.
And thank you for your contribution to this atomic clock in India, for sure. Since for last 5 years you've been building this, are there any personal anecdotes or any obstacles that you faced while you were building the clock in this?
Right. Well, there have been a lot of technological challenges as well because first of all, you need to have the facility to be able to build such a clock, right? So therefore, the challenge was, which was right ahead in front of me and my team, was basically to first build the infrastructure that is necessary, the lab and the equipment that is necessary in order not only to build the clock, but you got to test that at various phases. So, therefore, the test equipment was necessary. These were all some of the challenges. But then the management in ISRO, they were quite supportive in order to make this happen. And, once you have the backing, that's when, you can put a best foot forward and make this happen, right? So, yes, there have been technological and certain administrative challenges in the sense not everything can be done in a hurry, right? It takes its own time. So in that sense, to build the infrastructure takes time. But I
Correct.
must say, having said this is the fastest ever development in the entire world for a space clock.
That's impressive for sure. Since we were talking about getting funding for this, does the defense aspect of it come into play? Like we are talking about atomic clocks being precise, so one would assume that missile launches and everything also would be more precise if we start to use that kind of technology with it. Does that factor in when you do ask for funds or something, and a country is more, in general, not India, in general, would be ready to invest more in defense than space technology?
Yeah, because atomic clocks is a classified or a niche technology, right? The reason why it is a classified technology answers your question.
Definitely makes sense for sure. I think since you've worked a lot of different organizations in world, NASA, ISRO, and all, do you have any, from your personal view, any differences in the way people approach science or research in institutes outside India or in India? So let's assume I was to work at ISRO or NASA. What kind of different mindset one would have to take approach?
You said, would people approach science and technology any differently? The answer is no. Science and technology is still the same, right? But what is the drive behind doing that? That differs from place to place, as per my experience. Yes.
So what has been when you shifted from NASA to ISRO, or when you made a shift, what was your drive that changed personally as such?
In order to contribute for the growth of Indian science and space science and technology, so that was the drive. Why I got there, and I had a very good team, especially the young scientists and engineers. They were excellent. One of the best that I've worked with. The management also were very supportive because they had realized that this is a critical technology and it is useful for various applications, right? I mean, you name it, space, military, and there are n number of applications. So therefore it was pretty important to develop this technology within India.
Right. So I just wanted to ask, as atomic clocks are going into the forefront of cutting edge technology right now, what are the further improvements that are going to come up in your perspective? What are the advancements that can come up? What are the improvements that can come up in this kind of technology? And what would be the requirements that would make that kind of shift?
This is a fascinating question, I must say, because if there is already something, let's say there's an end goal and we have reached the end goal, what next will be the question, right? So if there is no next, then there is no drive, there is no interest, there is no curiosity, right? So with the clock world, I can say it's only a beginning, what we are seeing now. The reason I say that is because there are exceptional experiments and exceptional work that is going on how to further improve the atomic clocks and especially the optical clocks. Okay, the stabilities with the optical clocks, what we have been able to reach as of today is around 10 to the power of minus 18. Okay, now you don't even talk in terms of parts per billion or parts per 1000 billion or something like this is 10 to the power minus 18. That means if you have the frequency, if you divide that into 10 raised to 18 parts, that one part is the variation. Okay, now what it means is that it will not change by plus minus 1 second beyond the age of the universe, 15 billion years. Okay, so that is the kind of precision and stabilities that we have been able to reach with the atomic clocks. Okay, now what is the use of such clocks, right? That's the important question. What we believe in physics as constants, there are many constants that we study in our schools and in the universities, right? But are these constants really constants over a very long period of time? That's one of the very basic questions that people are trying to answer. It appears there's still, a lot of experiments are necessary in order to confirm this, but it already appears that these constants would also vary over, you know, many years, over the age of the universe, right? So therefore there is no such thing as a constant. But yes, given the context and given the time frame in which you're doing your studies, yes, it will remain unchanged, and therefore it can be considered as a constant. That is one thing. Second, the Einstein's equivalence principle, the gravitational redshift studies, and very recently, since last 2 years, people have proposed to measure dark matter using atomic clocks, right? Because think of it this way: the entire universe, we started off saying that it can be expressed in terms of space and time. Now, if you have your time very precisely, you can measure your space very precisely as well, right?
Yeah,
So
that
the
makes a lot of
fascination has
sense.
just started.
As soon as you mentioned that we are gonna have like we are gonna have such precision clocks, the question came up itself like, oh, then why do we need it? And you answered it perfectly after that, why we need it. But wouldn't it be a little bit of a problem to get funding for this? Currently, the kind of atomic clocks that we have can be used in a lot of practical applications as such. In this is not just in general to atomic clocks, but in general how, since you have worked with a lot of agencies, you must have insight that how do we drive funding part of it for projects that don't have direct practical applications for society as such. For example, study of dark matter, this is gonna be like 100 200 years down the line we'll have some practical implication maybe, but for current purpose this is just a curiosity, or yes, we want to explore universe. How do you drive that kind of funding levels from individual perspective and as a organization perspective?
That's a great question, because, we always ask that if it is just a basic science, how are we going to get funded? Because it is really going to cost a lot in order to study this, right? And because there is no direct implication, right? Why would we want to do that, right? Now, let me take, for example, of CERN. Okay. This is, we are now shifting slightly from atomic clocks, but it will answer your question. CERN, the Large Hadron Collider, where we accelerate the protons to very high speeds, 99.9999 uh, times a percentage the speed of light, and then you bombard these two particles, right? Now, you may ask that by doing so, how is it going to help the humanity? The same question, right? Because it's not a simple experiment, and this is going to cost, this had cost billions of dollars, right? Now, the the fact that we both are able to now talk on internet, world wide web, actually was an offshoot of, one of the technological developments that happened at CERN, right? Now, the internet would not have been invented had it not been for such complicated experiment. So in essence, there are lots of branches in a tree that you want to build. If your tree is pretty big, if your vision is pretty big, there are n number of branches that will come out, which will have innumerable number of applications that we don't know as of today, right? So therefore, exploring such huge aspirations in order to extend and enhance the human knowledge, and expand the boundaries of our capability, right? um, there will be a lot of applications that will actually offshoot from it. And similarly with clocks as well, there have been many different technologies that have actually come up. Plus, the drive now is, one way it is to make better and better clocks. Okay. Second, these optical clocks have been part of the laboratory clocks until the last 2 3 years. Now, how to bring these clocks into the real world? That means, can we put this clock in a car or in a van and then take to different places and do the measurements? For instance, Recently, I came across the talk by Hidetoshi Katori. Um, he is a professor in Tokyo University in Japan. It's fantastic what sort of advancements have happened in terms of the portable optical clocks from his lab. So there are lots of offshoots from such technologies.
This might sound very capitalistic, which I don't want it to be, but do you see any private players entering this market since it is classified till now? But you would assume that someday a private person, a private company or something would want to venture into this area. So do you see anything like that?
Yeah, yeah. You'll be surprised to hear that there are as many, if not more, companies which are making atomic clocks as the research institutes. So, therefore, the job market is fantastic.
Okay, that actually is
Already there are many
makes sense.
companies, right?
That makes
And
sense.
these companies are also doing different and newer kinds of clocks, uh, finding newer applications. So, one of the application, for example, of such clocks, in order to find the oil reserves at the underneath the sea, because GPS signals wouldn't be able to penetrate the oceans. So therefore, if you need to do any echo measurements in terms of ultrasound, that's echoing from the ocean surfaces, right? Then you need better time. Where will you get the better time from such clocks? You know, so that's one of the applications, but there are many applications in the sense, for instance, the small satellites, CubeSats. If you need better time on board these CubeSats, such very small clocks can be used as well.
What about quantum computing as such? Like, since we have heard a lot about atomic clocks being used there also, since it's very precise sensors and everything. So, is that the area that the companies are looking forward to? Because I've seen like Google, IBM being working on qubits and all, and they are trying to implement. They are basing it on atomic clocks instead of computer chips. So,
Now, because the base idea, in order to take the spin states, as I mentioned, will still hold good when you want to do quantum computation. So, therefore, the technologies that are used to develop atomic clocks are almost directly applicable. Apart from the computation part, right? The um, the base for where you do the quantum processing, okay, um, that's the technology is almost the same. So, therefore, yes, um, the all the know-how and the nuances of building an optical clock is very much applicable towards quantum computing, and there is like quantum networking. So therefore, in US now it's a buzzword that it's quantum 2.0. Okay, so which means the idea of all these basic understanding of quantum, how are you going to move towards certain applications of quantum computation, atomic clocks, because atomic clocks, you have all quantum physics in that, right? So, and then the quantum communication, secure quantum networking. So all this is now part of quantum 2.0. So yes, to answer your question, it's same technology and similar idea, and therefore, coming back to the question of jobs, if you learn these basics, not only the clock companies are there to hire you, um, you can go and do quantum computing, for example.
It's actually quite a good news that like you said, there are a lot of job prospects for people who are in this field, not just in academia but also in industry. So, like, I think this will be our last question. Would you like to add something for students who are, looking up to you or this field to make career in, or as a researcher, like some advice
Yeah,
or insight?
absolutely. Um, that's one of the driving factors, to be honest with you, why I joined the university. In order to motivate these students from the young age to move towards this particular field. Okay. So, because as I mentioned, this is not only physics, but a lot of engineering. Okay. 70% of what I do is engineering, right? So, therefore, there are many companies and they're just waiting for students to come join such companies, right? What I would advise a student in this, if they're venturing or having some drive to get into these fields, is focus on your basic studies. It could be physics, it could be electrical engineering, mechanical, doesn't matter what you're studying, but focus on those basics, strengthen that. And then, when you make any shift towards, it's called PNT, positioning, navigation, and timing. When you want to make a shift towards this field, all the basics that you have studied will surely come into play. Okay. So, therefore, study what you're studying with full vigor and a lot of dedication. Then moving towards this field, definitely, one need not worry about jobs, but the drive or the motivation should be, how can I contribute? Okay. If you have that drive, this is what I would like to advise students, that the drive should be, how can I contribute? Okay. Because with that drive, you would automatically enjoy what you're doing, right? If you enjoy what you do, then job is only a consequence of it.
This was a conversation from the fifth season of Zeroing In, the Science Podcast, where we talked about the fascinating science behind building the most precise atomic clocks, engaging the current status of such technology in today's world. We are very grateful to Professor Bandi for sharing his nourishing insights, excitements of the field, and the love for the subject in a lucid conversation on behalf of the Zeroing In team for this season. Thanks a lot for listening to this episode. We'll be back with a new episode next week with further interesting questions and conversations with eminent Indian scientists from across the world. If you'd like to listen to more such discussions, you can visit us on zeroingin.org. Follow us on our Instagram or Facebook handles at the Zeroing In Podcast for the latest updates.